A curved section of a curved section of track on an Olympic velodrome has a radius of 50 metres and is banked at an angle of 42 degrees to the horizontal. A cyclist of mass 75 kilograms is riding on this section of track at the design speed. Calculate the net force acting on a cyclist at this instant if they are riding at the design speed. Okay, so you probably don't need to do this in this case, but it's always a good habit to get into. I'm drawing a diagram. So, here is our track, our cyclist. There's there. Oh, it looks like a unicyclist. Never mind. There's our cyclist. Now, one question that always comes up on exams for some reason, they always love asking you this, is label the forces acting on this cyclist right now. Okay, so what are the forces acting on him? Gravity? Which direction?
Directly downwards.
Directly downwards. So mg is there. What else?
Normal force.
Which direction?
Perpendicular to the slope.
Good. There is a normal force perpendicular to the slope. And so the vector sum of those is going to be our net force.
Do you also have to label that one?
It depends on the question. You won't lose any marks for labelling that one. Okay, so there's our diagram. Okay, normal force perpendicular to the bank, mg acting downwards, and our net force is acting inwards. So what do we want to do? We want to calculate, what are we looking for? The net force. Okay, so we can use the equation we saw before. Tan theta equals F net on Fg. Now this is a pretty straightforward rearrangement. If we want F net as the subject, just multiply both sides by Fg, we get F net is equal to Fg tan theta. Okay, Fg, the force of gravity acting on our cyclist, is 75 times 9.8. So remember, Fg is just mg. 75 times 9.8 times the tan. What's our angle? 42. If you're faster with a calculator than I am, go for it.
Oh, it's like 6.6 times 10 squared newtons.
6.6 times 10 to the 2?
Yeah.
Like that? Cool. So what's that? 660 newtons.
Yeah, approximately.
Yep, perfect. All right. Thank you very much. So our net force acting on our cyclist is 660 newtons. In which direction? Inwards. Good. Inwards. 660 newtons acting towards the centre of the track. Good. All right. Calculate the design speed for this section of the track. Okay, this isn't too bad. This is just plugging numbers into that equation we saw before. So the equation, V equals Rg tan theta, square root of all that. So what's our R value?
50.
50, good, our radius is 50. G is 9.8, and we know tan 42. We want the square root of all of that. Now, occasionally this question comes up on an exam, people get it wrong, and usually it's because they forget to take the square root of it. So, don't forget that bit. 50 times 9.8 times the 10 of 42. Did we get 441.2? Okay. Seems really fast, doesn't it? No, I didn't square root it. I did that just to show you what not to do. Right, so before when I said, you know, people forget to take the square root of that, that was just to see if you were paying attention. All right, good work, team. So, 21 meters per second.
Yeah, that's the only way to do it.
That seems much better.
Since that's